Yeah, welcome everyone for today's presentation. Today we have Professor Daniel Oron from the University of Sydney. He's going to talk about the traceability of hard scheduling problem, a parameterized, uh, parameterized complexity approach. So Daniel is a professor of operation research in business analytics at the University of Sydney. He holds a PhD in operation research from the Hebrew University of Jerusalem, and his research of expertise is in combinatorial optimization with a focus on the scheduling theory. He is widely known for his work on multi-agent scheduling, resource allocation problems, serial and parallel batching model, and production problems under varying conditions. So his work has been published in leading operation research journals, and he is currently serves as an associate editor in the Journal of Industrial and Management Optimization. So over to you, Daniel.
Okay, thank you very much for the introduction and for the invitation to present. And as mentioned, I'll speak about the tractability of hard scheduling problem. And I'm going to look at a parametrized complexity approach, which is something that's relatively new, definitely to me. So I'll just speak a bit about complexity theory and scheduling and how hard is NP hard. So clearly, most of the people here are optimization people. So I'm pretty sure that you know quite a lot about complexity. But for me, it was a pretty new thing to hear about parametric complexity or parametrized complexity, which is kind of a way of looking at complexity theory in a finer way, or breaking down the different classes and the hard problems or a polynomial time problem into smaller slices and actually gaining more insight. Because really, question is, how hard is a problem? Some problems are easier and some problems are harder. Hard problems weren't created equally, and that's something you can see in a lot of combinatorial optimization problems. Now, I've chosen two scheduling problems to demonstrate this, minimizing maximum lateness and maximizing the number of on-time jobs, both on a single machine. I'll describe how easy those problems are when you have general due dates, but when you have something called generalized due dates, and I'll say what generalized due dates are, suddenly the problems become really hard. And it's counterintuitive because it's usually the other way around. When you're given more flexibility, the problems usually become easier, but here it's this extreme case where easy problems become hard when you're trying to actually make them even easier. And I'll speak about some algorithms for these problems. I'll speak about FPT algorithms, which I'll explain what they are, but they're fixed parameter tractable algorithms for the two problems. I have to mention this is joint work with Gur Mosheyev and Dvir Shabtai. Gur is from the Hebrew University of Jerusalem, and Dvir is from Ben Gurion University in Israel. Both of them are co-authors, longtime co-authors, but very good friends as well. And this is joint work with them during one of my visits at their universities. So everyone knows what class P and what class NP are. And again, it's conjectured that P and NP are distinct classes. That's one of the millennium problems. I think the proof has eluded researchers, and probably I don't think that there is a proof. But still, it's an open problem and is still challenging for researchers in the field. A parametrized complexity it originated sometime in the 90s. And I think the defining moment was when a mathematician and a computer scientist, Rod Downey is the mathematician, and Michael Fellows is the computer scientist. They met at a conference, and they weren't happy with the current state of complexity theory, and they started discussing about regarding methods of how to look at complexity theory through a magnifying glass, meaning on a finer scale. And that's the birth of a parametrized complexity. Their book was only published, I think, 9 years later in 1999, and that's the first source on parametric complexity. But I think the idea was born at a conference in New Zealand in 1990. I always like to mention that there's an Australian angle here because Rod Downey did his PhD in Monash. He's an Australian and New Zealand national, but I think he spent most of his time in Australia and studied here. And Michael Fellows, although he's American, he spent many years working in academia in Australia, and he's a naturalized Australian. He did move to Europe in 2016, and he's now in Norway, but he did spend most of his productive years here in Australia. So kind of an Australian, I think, alliance that created parametric complexity, and I think we should be proud of it. Now, in parametrized complexity, we've got different classes. I won't go into exactly all the classes, but within what we define polynomial time, they have classes which are called FPT and XP. When they move into more or harder problems, then there are classes called W and later on para and P. But I'll just focus on classes FPT and XP. So if we've got a problem and the problem size is defined by n is the number of inputs. So in a scheduling problem, that would be, say, the number of jobs that are presented to the scheduler. K may be an upper bound on the richness of parameters. Usually, when we look at a scheduling problem, each job has a processing time. So if we have n jobs, we're assuming that we've got n different processing times, or we solve the problem under the assumption of n different processing times. But that's not really the case in a practical sense, because if the number of jobs increases from 10 to 1,000, for example, we won't have potentially processing times which are close to 1,000 or even in the hundreds. We're going to get processing times which are within a reasonable range. So for example, if I produce a certain item or I provide a certain service to customers, I'm not going to have processing times which are equivalent, or the number of processing times which is equivalent to the number of customers, because the customers fall into certain categories. So maybe I'll have 5 different processing times, so I can bound the number of possible values for a parameter by a constant k. Now, if I can develop an algorithm which has a running time of f of k, where f is a general computable function of k, times n at the power of O of 1, then I've developed an algorithm which is called fixed parameter tractable. So for example, if I've got 1,000 jobs and my algorithm needs some f of k times n cube, still that's going to grow very slowly. So if I increase the number of jobs to 10,000, it's still going to be a very fast algorithm. And therefore, it's almost polynomial. It is polynomial for a fixed k. Class XP is kind of like slice-wise polynomial, because it's still polynomial when k is bounded, because it has a running time of n at the power of some function of k, a computable function of k. But clearly, as n grows, this may grow faster, because with the fixed parameter tractability algorithm, my f of k is just a multiplier. Here it's a power in class XP. So this is a slower algorithm and therefore not as efficient. So I'd like to know where I can classify my algorithms for NP-hard problems, but where I fix the bounds on parameters, and therefore am able to develop an algorithm which is efficient. But the question is, how efficient from a computational standpoint? So I'll just speak a bit about due date. So in classical scheduling models, due dates are just assigned to a job. So for example, I've got 10 orders from customers, and each customer is quoted a due date, and I have to produce an item or provide a service by that due date in order not to pay a penalty. Often there are penalties for a early completion, that's just earliness penalties, or for late completions. And there are different types of penalties, but in principle, a due date is associated with a job. So each job has its own due date. Now, this is the case for most systems, but not for all systems. And in 1986, Nick Hall, who's a big scheduling researcher, introduced the notion of generalized due dates. And their due dates aren't associated with a specific job, but they're associated with a job which is processed in a certain position. And this is relevant for areas like project management, infrastructure, or maintenance. A good example would be, say, for example, if we've got a bus depot and there are 100 buses which require some kind of maintenance, each bus requires a different service. Maybe one bus just requires some oil change, but another one requires say a change of oil, but also some tires and so forth. So they each have different requirements and therefore different processing times. But the operator of the bus company or the operations manager doesn't really care which bus is ready at which time, but rather the number of buses ready for say Monday morning. So maybe there's a requirement that by 8 a.m. there are 10 buses which are available for service. And then by 10 a.m. there is a further 5 buses which are available, and so forth. So clearly we're not interested in the identity of the buses. So each bus doesn't have its own due date, but rather due dates require a certain number of jobs to be ready by that time. And that's the whole notion of generalized due dates. So usually generalized due dates are much easier than just due dates in general. If we look at the problem of total tardiness, so if anyone has done any work on scheduling, they'll know that total tardiness is an NP-hard problem. It's one of the classical NP-hard problems proven by Joe Leung, who's a very big scheduling guy, in 1991 as part of his PhD, and therefore it is a hard problem just with a job-dependent due dates. With generalized due dates, it's super easy. With GDD, you just order the jobs in smallest processing time first order, meaning you put the smallest job first or the shortest job first, then you sequence the job with the second shortest duration and so forth. And the longest job is at the end without any idle time, and you obtain the minimum total tardiness. So with GDD, it's a very easy problem. It's just solved in O of n log n, whereas total tardiness in general with job-dependent due dates is NP hard. There is a dynamic programming algorithm there, quite complicated and clever, but you do have to work quite hard in order to solve this problem to optimality. So this is just an example that GDD problems are usually easier. I've got two examples here of jobs with problems which are harder when you assume generalized due dates. So the first problem is minimizing the maximum lateness, or I should probably say minimizing the maximum absolute lateness. And the idea here is that if you've got a certain due date for a job, if it's completed before its due date, then this would be your earliness. You're a bit early. And if it's completed after its due date, this whole length here would be its tardiness. So when we say absolute lateness, lateness is measured by the completion time minus the due date. If we look at absolute lateness, then clearly it's either the tardiness or the earliness, whichever one occurs. One or the other occurs, or maybe none of them occur if you finish the job exactly on time by chance, or if just you have a schedule where jobs are completed on time. So this is a very easy problem with due dates. With due dates, you can, with job-dependent due dates, you can simply create a schedule which is earliest due date first. You take the job with earliest due date and you sequence it first. Then you take the job with the second due date, the second smallest due date, and sequence it second, and so forth. And then you just have to decide on the start time and finish time of each job. The finishing time will simply be the start time plus its duration, and you solve a linear program there. And we all know that you can solve linear programming in polynomial time, and therefore you can solve this problem in polynomial time for job-dependent due dates. It turns out that with generalized due dates, the problem becomes NP hard. So the other way around, my expectation when looking at this problem was that I'm actually going to get an easier solution, but at the end of the day, the problem turns out to be NP hard when you allow for generalized due dates. So the idea is that we're given a set of jobs, J1 through Jn, and they're characterized by their duration, by their processing time, Pj. Now, I know nothing about the due dates. The due dates are not related to the jobs. So I get a set of due dates, delta 1, delta 2, through to delta k. I've got, in general, k due dates. Each due date is associated with a number of jobs that have to be completed by that due date. I can have even n different due dates. And then for each job, well, first I have to decide on a job permutation, which is optimal. So that would be my pi, my job permutation. And after I have a permutation, which I find is optimal, I have to set start and finishing time, or a processing window in simpler terms, for each one of my jobs. Now these processing intervals, they can't overlap, but because of the assumption in scheduling is that a machine can process at most one job at any given time, I'm also assuming that preemption is not allowed. So I'm not allowed to start the processing of a job, then stop it for a certain time interval, process a different job, and return to my original job. Once I begin the processing of a job, I have to complete that job before processing any subsequent job. So whenever my index is a regular index, I'm referring to the job identified there. So J1 would be the first job in my set, or J2 would be the second job in my set. When I have the index in brackets, I'm saying that it's the job that's in that position. So J1, but one in brackets would be the job that's first in my sequence of jobs. J in brackets 2 would be the second job in that sequence, and so forth. Now, I am allowing for idle time. So if I know J1, I know when J1 starts and when it finishes. The only information I know about the start time of J2 is that it's sometime after the completion time of job J1. So I'll use S for the start time of a job, and I'll denote by C the completion time of a job. So it turns out that the problem of minimizing the maximum absolute lateness, a really easy problem when assuming generalized due dates, is super easy when I've got just a single due date. But when I've got two due dates or more, the problem becomes NP hard. So a problem that with even end due dates is easy with regular due dates, job-dependent due dates becomes NP hard with the generalized due dates, even when we only have two of these generalized due dates. And that's super interesting. Well, I think at least for scheduling people, it's very exciting. So the idea and the proof here is that you can reduce this problem to a partition problem, an equal size partition problem. I'll just mention how do you solve the single due date problem. With the single due date, it means that all the jobs are associated with the same due date, and therefore any sequence where the largest job is first, and then all other jobs are processed in arbitrary order, that would be an optimal schedule. You only have to decide where that schedule starts and where it finishes, but you can do that just by moving your schedule and making the earliness equal to the tardiness. So you have a very large job, then you have a sequence of other jobs, and you put the due date exactly in the middle so that the tardiness on one side is equal to the earliness on the other side. And therefore, you've solved the problem. It's solved in O of n because you just need to scan through a whole array of jobs and find the maximal processing time job. On the other hand, when you've got two due dates, then the problem becomes NP hard. The idea is just to reduce it to a two partition problem. And the way you do that is you create a problem that has 2t plus 2 jobs, so n equals 2t plus 2. Jobs 1 through 2t are the input of our partition problem. They're A1 through A2T, and we know that their sum is equal to 2B. And the question is whether we have a partition of these 2T jobs into two distinct sets, whereby the sum of the processing times in each set is equal to B. And then we have two jobs which have processing time 2B. And we set our due dates, delta, to be delta 1 equals 2.5b and delta 2 equals 5.5b. And we require t plus 1 jobs to be completed by the first due date and t plus 1 jobs to be completed by the second due date. I won't go into the details of the proof, but it's a pretty easy proof. It's kind of very elegant, but it's very simple. The idea is that the large jobs have to go into time windows 0 through to 2b and time 3b through to 5b. Otherwise, they'll violate our bound for the maximum lateness, which is b over 2. And therefore, all the other jobs have to fall in between. And it's easy to show that the other jobs fall into two groups, and each group has to sum up exactly to B. Otherwise, we'll violate this bound as well. So it's a pretty easy proof, but it's quite elegant. So the idea here is that if we've got just need D possible due dates, and each one of these due dates is associated with a certain number of jobs, and in total we've assigned all n jobs a due date, then we're interested in finding a polynomial time solution, which is, it's not really a polynomial time algorithm, but it's a polynomial time algorithm that's bounded by a polynomial function of n multiplied by some function of n of d. Okay, so I'm going to look for something that's bounded by a function of n of d multiplied by something that's a polynomial function of n. That's the idea there. So I can prove that a solution will include no idle time, and I can also prove that when I break down the jobs into a needy different sets, each one associated with one of the due dates, I'll always process the largest job first. So the reason for that is, if this is a due date and I've got a set of jobs there, if all the jobs are processed in a block here, it doesn't matter how they're ordered, the tardiness or the maximum lateness will be defined by the last job. If they're all early, then the maximum earliness or the maximum absolute lateness will be defined by the completion time of the first job. And therefore, it's always good to put the first job at the beginning of the schedule. And if it overlaps, then again, it's easy to prove that you would always like the first job to be the largest job in that set. So my goal here is to actually come up with a partition of n jobs into needy different groups. I'll always put the largest job allocated to each group first. all other jobs, I'll schedule them in an arbitrary order, and then I'll glue together all of these blocks and schedule them as a single schedule. So that's the idea there. And the idea here is that once I've got the partition into these needy sets, if I can do that, then once I create that block, all I have to do is decide where each block starts and finishes. And that's quite easy to do. I just define a few variables. Z is just a dummy variable that will help me solve the problem, and it will determine my objective function value. I'll denote by alpha I the maximum size job in each one of these sets. So I'm going to have alpha 1 being the size of the largest job in J1. Alpha 2 will be the largest job in set J2, and so forth. And PI is going to be the total processing time of all the jobs which are allocated to each set. So P1 will be the total processing time of all jobs contained in J1. P2 will be the maximums, the total processing time of all jobs in J2, and so forth. If I know how to create these sets, then I can easily solve the problem of when each set starts and each set finishes. I'll just say that the starting time of set I is larger than or equal to the starting time of set I minus 1 plus its processing time. That's pretty easy. Then I'll say that my objective function is larger than Si plus Pi minus delta I. This is the amount by which the set is laid. The last job in the set is laid. And then I'll say that Z is larger than or equal to the amount of time by which the first job is early. So the first job finishes at time Si, the time that the whole block of jobs starts, plus alpha I, because I've put the largest job first in each one of these sets. And then delta minus that will give me the earliness. So I'm saying that my objective is larger than the earliness of the first job in each set, and it's larger than or equal to the tardiness of the last job in each set. And I just have a condition that the sets don't overlap. And then I solve this problem. So an LP solves my problem. The question is, how do I choose these sets? And these sets, in essence, they just need, each set is a unique vector of size 2 needy, where the first needy entries are the size of the set, and the second set of entries, needy entries, are the size of the maximum job in each one of these sets. And I can build the whole set of vectors by dynamic programming. So I know exactly how many jobs have to belong into each one of the sets, and I can create a dynamic program which will allocate jobs into these sets and update. And the process, well, the process is pretty long, but it's still bounded, or it can still be done in polynomial time. So I probably won't get into the way this is the construction of the vectors or the whole family of vectors, which I have to consider and solve an LP for each one. But it is in a paper that we published on this topic. It's a bit tedious, but it still works. Now, the more interesting issue is, now I'd like to consider not only bounding the number of due dates, but also bounding the number of possible processing times. So I've got n jobs, but my claim is that when n grows, the number of processing times doesn't grow as well. So I should have a set P1, P2, up to P NP. And each job is going to have a processing time, which is one of these NP values. The same is true for a due date. I've got delta 1, delta 2, and delta ND. So I've only got this number of due dates. So as the problem grows, the input of the problem grows, it actually doesn't really grow. I'm just updating the number of jobs that have P1 as their processing time, the number of jobs that have P2 as their processing time, and so on. So I've got a list of size NP. It doesn't grow. It's not a list of size n. As you add a job, you're just increasing the number of jobs with a P1 or the number of jobs with processing time P2 and so forth. You're not really increasing a list. You don't need another row in your list of jobs. You're actually just updating the same list you have by increasing the number in one of the entries. With the due dates, it's exactly the same. You're just saying, well, I need another job completed by a certain due date delta 5, for example. But you're not adding another due date. You're just saying which due date should have another job finished by that time. So as n grows, the problem actually remains the same size. It doesn't grow. So in order to prove that the problem is in that class FPT, fixed parameter tractable, I need to come up with some kind of formulation. And in this case, it's a mixed integer linear program that it has a number of variables that, again, doesn't grow with n, but remains fixed in the number of variables. So that's the idea there. If I can formulate an MILP or any type of algorithm which runs in O of ND, NP, or some function, but polynomial function of these, but not in O of n, for example, then I can show that this is fixed parameter tractable. So what we did here is we tried to formulate a mixed integer linear program. We know from a result from 1983 by Jan Karl Lenstra that if you can formulate a mixed integer linear program which has a fixed size and doesn't grow with your input, then you can show that a problem is a polynomial for a fixed parameter value. So the idea was to look at the following decision variables. We know that we've got delta 1 through delta ND as our due dates. Then we needed to know how many jobs are associated with each one of the due dates. So these are M1 through MND. Clearly the sum of these M's, the sum of the entries of the vector M, is equal to n. That's the number of jobs we have. So every time you add a job, you increase one of the m's. Then we have P1 through P, NeP processing times, distinct processing times. They can be any value. But then we've got N1 through NeP, and these are the number of jobs with that specific processing time. So again, when I increase my input, I'm just updating the NI's there. So for example, if I add a job and I decide that its length is going to be P1, I just increase N1 by 1 and so forth. So I have all the information through these 4 vectors, but note again that their size is limited. So increasing the number of jobs doesn't increase the size of these vectors, just changes the entries of these vectors. Now, without loss of generality, I'm just assuming that P1 is the smallest processing time, followed by P2 and so forth. And the same goes for the due dates. They're ordered in increasing order, just for the sake of convenience. So if we define a variable xij, which is an integer variable, telling us how many jobs with processing time pj are allocated to the first due date. Then if I sum up over all the xij's over all the due dates, I should get n jobs. But also, if I sum up over all the xij's over all the types of processing times, I should also reach n jobs. So I kind of get a really nice structure there for my mixed integer linear program. So here, I'm just ensuring that I get enough exactly the number of jobs for each category. So if I sum up over a I, then I know that I'll get nj. If I sum up over I and j, I get n. If I sum up over I get the nj's. If I sum up over j's, I get the mi's. So we need this set of constraints, but again, note that the number of constraints doesn't grow with n. It's just these numbers and these numbers grow, but the number of constraints doesn't change. It remains the same. Then, given that allocation, I still have the same condition that I want the starting time of the next set of jobs, the one associated with the next due date, to be larger than the completion time of the previous set of jobs associated with the previous or the current due date. So I just sum up over all the processing time of the previous group and add that to its start time. So that makes it very easy. And then I've got 2 constraints of the Z constraints, a set of constraints for each one of my blocks, sets of jobs, that Z is larger than the earliness, but also larger than the tardiness. And then finally, I need to keep track of which is the largest job that's in each one of my groups. And this is where our challenge was. Up to here, it took us 20 minutes. From this point on, it took like 4 days to come up with the exact way of finding or formulating the maximum size job in each one of our sets. We just said that, say, for example, alpha 1 is smaller than P1 plus some binary variable which sums up over P2, P3, P4, and so on. But this binary variable is bounded by the xij's. So essentially, we're getting something of the sort that alpha 1, for example, is smaller than P1 plus some y1, y2 maybe times p2, but then alpha 1 is smaller than or equal to p1 plus p2 plus some y3 times p3 and so forth. Now, the idea is that alpha 1 is always smaller sorry, here we can do something like this. So alpha 1 is always smaller than p1, which is the smallest processing time. But if we do allow jobs of type 2 to exist, then the alpha 1 is smaller than p1 plus p2, and that becomes a loose constraint. And suddenly alpha 1 is bounded by p2. But then we've got a y3 plus p3, and in a rolling way, we created a lot of sets of these constraints, but again, bounded by me d. But there's a set of constraints like this, which allow the maximum processing time to grow if downstream there's some binary variable which allows the constraint to become loose, and that binary variable is bounded by the actual variable, which tells you what the number of jobs of that type is. So if the number of jobs of that type is equal to 0, then clearly the binary variable is set to 0, and therefore you get a tight constraint, say on P1. And that was the idea of this whole set of constraints. So this MILP solves our problem when the number of due dates is bounded by a certain value, a fixed value, and the number of possible processing time is also bounded, but the problem itself continues to grow. You still solve exactly the same problem. In terms of computational time, it's going to grow slowly because the numbers are going to be bigger. The NJs are going to be bigger, the MIs are going to be bigger, and so on. We didn't really test this. Say we could have coded problems in Gurobi and run them, but I'm pretty sure that the growth rate here would be super slow, whereas we would be able to solve a very large number of a problem with a very large number of jobs because of this condition that we're fixing the number of possible values for both our processing times and our due dates. So here we conclude that the problem itself becomes NP-hard very quickly, but when you're able to bound the number of due dates and when you're able to bound the number of due dates, the problem becomes easier. Then when you're able to bound both the number of due dates, but also the number of processing times, the problem becomes even easier in terms of computational time. And that's a really nice solution. And both of these solutions fall into the fixed parameter time. Running a bit late, I was expecting to go over the second example. I'll just describe what the second example is. The second example is the number of just-in-time jobs. So with a number of just-in-time jobs, you're actually given a set of due dates, and you want to solve a problem where you're trying to finish as many jobs as possible exactly on time. So if you're able to finish a job on time, you get rewarded for it. And if it's even 1 second early or 1 second late, you don't gain that reward. Now, the problem with regular due dates, it's super easy. For regular due dates, you just calculate dj minus pj. and you order the jobs in increasing order, and then you try to put the first job in if it works, you leave it if it doesn't work, you throw it out, and so on. So it's solved in O of n log n. If you want the weighted version, it's a bit more complicated. You just sort the jobs, so weighted, you just sort the jobs, I think in increasing order of what, no, sorry. You sort the jobs in EDD, and then there's an easy dynamic programming algorithm which works in O of n squared. So this is a really easy problem when you've just got a job-dependent due dates. It turns out that when we're looking at generalized due dates, again, we've got a pretty nice proof that even with two due dates and the unweighted case, the problem becomes NP-hard. And we do pretty much the same type of analysis. We play around with a parameter R, which tells us how many on-time jobs we have. So we run R between 1 and the number of due dates we have. And then we set all the possible vectors, L1 through LR, which are a list of the due dates, which a job completes exactly on time there. So for example, this list can be delta 1, delta 5, and delta 8. That would mean that 3 jobs are completed on time, and on which due dates? 1, 5, and 8. Clearly, this vector could be of size 1, it can be of size 2, size 3, or up to size ND, but it's pretty easy to show that the number of such vectors, because they're ordered sets, then the number of such vectors is bounded by a polynomial function of ND, and therefore, if we can come up with an algorithm which solves the problem for each given vector, then we can show that the problem is fixed parameter tractable. I won't go through the algorithm itself, but we do have a dynamic programming algorithm for the unweighted case and for the weighted case. And then we have another mixed integer linear program for the combined parameter. We're able to show that for the combined parameters, meaning that we bound the number of processing times, but also the number of due dates, we can solve the problem in using a mixed integer linear program, which has a number of variables, which is O of NP times O of ND. This is number of variables. So our conclusion here is that we've taken two problems that are super easy in their classical sense, but when you give the scheduler some flexibility and you tell them, well, I don't really care if customer 1 has a due date and customer 2 has a due date. I just want you to finish service for one of the customers by time 5 and for the second customer by time 10. Suddenly the problem is really difficult. If you ask me to finish customer 1 by time 5 and customer 2 by time 10, I can solve the problem. But if you tell me you choose which customer gets which due date, suddenly becomes hard. It's both in the case where I'm trying to minimize the absolute lateness, and that's a good measure for the level of service, but the level of service which the worst customer gets. So I can kind of speak of fairness here. I want to, the person who's the most disadvantaged, I want to focus on them. So that would be a measure of fairness. So when I'm trying to minimize the unfairness, I run into problems when you actually give me an easier problem. The second example is when I'm trying to finish jobs exactly on time. So that would be just on time jobs. And there as well, when you allow me that flexibility and you say, I don't care which jobs you finish, but try and finish as many jobs as you can exactly on time so that as many customers are happy. I'm actually struggling when you tell me which customer has which due date, the problem becomes much easier. What I can do is when the problem really grows and I know that the number of due date is going to be bounded and the number of types of product is going to be bounded, meaning processing times are bounded, then I can come up with efficient algorithms. These algorithms run kind of in FPT, which is slice-wise polynomial. So it's almost polynomial time. It's very close to polynomial time. We say that it's polynomial for a fixed parameter size. So those are the conclusions we take. Again, there's a lot to be done in this area. I kind of felt I was late for the party because a parametrized complexity is relatively old in, say, OR age, not in mathematics age, but in OR age, it's relatively old. It's 25 years old or 30 years old. But in scheduling theory, it's only about 6 or 7 years old. So I was late to the party, but not too late. So now I'm making ground and I am looking at other problems, but I think it's mainly interesting to look at problems where some cases are really easy and some cases are really hard. And that was my attempt with these two problems I introduced. Hopefully, it wasn't too fast or too abstract, but yeah, that's pretty much it.
Thanks, Daniel, for the presentation. It was interesting as topic and also great conclusion for the application of that you are going to do.